Good evening. Professor Rolf is on a trip, so I'm going to be talking to you today about physics. So he told me you've covered peaks and interference in general, right? So if that's true, today we have to talk about tiny waves. And it's another application of a simple math. Beats is the result of addition of two waves with very similar frequencies. If we want to add two waves with exactly the same frequency, what we get in the result under certain circumstances is a standing wave. From a mathematical point of view, you would have to add two harmonic functions. For example, sine and another sine, or sine and cosine, two cosines together. So, but you don't have to do that. If you had it done, the result would look similarly to this. This function has two parts. One part is related to time only, and another part is related to location only. So what we have here is two waves. One is traveling to the left, one is traveling to the right. They both have the same amplitude, they both have the same frequency, the wavelength. But when two waves encounter each other, well, what is happening in the end is this. The actual shape of a wave on a string, for example, the total displacement, always equals to the sum of individual displacements. So in this simple situation, that's the result. And what does this part tell us about? If you imagine a string, well, of course, there's x-axis in a certain direction, normally pointed to the right. So at different locations along that axis, this number has a different value. For example, at x equals 0, sine of 0 is 0. So at x equals 0, this coefficient equals 0 at all times, which means for this particular wave, at x equals 0, there is no motion at all. Never. However, if we move a little bit to the right or to the left, x is not 0 anymore. So at that particular location, this coefficient has a new value. At that particular location, this value doesn't change. So at that particular location, motion is happening, limited by this value. So for that particular location, this coefficient describes the amplitude of that motion. And at some point, when k times x equals pi over 2, sine reaches 1. That's the maximum value for the sine. When this sine equals 1, the whole coefficient equals 2 times a. So at that point, the motion is happening with a double amplitude comparing to each individual wave. And what's happening after that point? Well, when sine reaches 1, after that it goes back to 0. So at some point there is no motion at all, then motion with some amplitude, larger amplitude, even larger amplitude, maximum amplitude, smaller and smaller and smaller and smaller, and back to 0 again, and again, and again, and again. So the amplitude of these oscillations depends on the location, and the shape of this wave would look like this. location number 1, for example, x equals 0, there is no motion at all. There is another location like that, and another, and another. Points like that we call nodes. And at some points, the motion is happening at maximum possible amplitude. We call them antinodes. And this is the result of two waves traveling in opposite directions. One wave is traveling to the right, another wave is traveling to the left. When they overlap, the result depends on the location. No motion, maximum motion. No motion, maximum motion. Here, this point. These two waves always out of phase, completely out of phase. So the completely destructive interference is happening at this point. And at this point, these waves both have maximum amplitude A in the same direction at some point. So node, antinode, node, antinode, node, antinode. That's what a standing wave is. Well, of course, we have to learn how to describe this situation mathematically, but first let's take a look at several standing waves. This is one of the possible situations. Wrong one. Here. Does it look like a standing wave? Not really. You see, this standing wave is very stable. So, first fact is, to generate a standing wave, we should fulfill some conditions. What kind of conditions? We'll learn later. This looks like a pretty neat standing wave. Yeah. Now it's broken, but now we have a different kind of shape. Node, 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 antinode, 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 antinode. I can change the tension of the string and try to generate a different kind of wave. The tension is related to what? To the speed of the wave. The speed is related to frequency and wavelength. So the shape might depend on those variables. How will we learn soon? Well, this is just a toy. You can generate, anyone can generate a standing wave if you have a guitar, for example. Well, sorry. If you excite the string, what is happening? It generates a spinning wave, and that wave actually pushes on air molecules around, and that's why we hear it. If we suck out all the air from this room, we couldn't hear it. But that doesn't mean the standing wave is not generated. It's still on the string. So there are two different things: how to generate and how to observe. For a sound wave, we need the medium, but we don't have to use any medium to generate this wave on the string. You can take a regular spring. Well, of course, first of all, you can just make a pulse. See, one pulse is traveling, it gets reflected. You probably know that depending on the condition at the end, the pulse might be reflected inverted, or it could be reflected keeping the original orientation. So for this situation, when the string is attached to the hook, the end of that string is fixed, so we can generate several pulses traveling to the right, they get reflected and inverted and go back. And as a result, for specific frequency I generate, we can observe a standing wave. This standing wave has, well, two nodes, and 1, 2, 3, 3 antinodes. But if I try to move faster, at another specific frequency, I can generate another wave. The same length, the same spring, but different shape. Why and how can we calculate the frequency which we should apply to generate a specific shape? Well, we'll talk about that. But this, if you look at this shape, that's the longest wavelength we can generate in this wave. We cannot make any longer, because a wave always has particular parts which repeat itself. And this is exactly a half of a wavelength. One half, another half. What we see here is exactly one half of a wavelength. I can make only waves with a shorter wavelength, like this, for example. Or, well, you see, I have to generate the motion at the source of the wave with a specific frequency. Otherwise, there is no standing wave generated. Well, we call it a different name. We say sometimes that the resonance situation is reached. Well, resonance basically means some specific conditions are fulfilled. Well, some of you might have seen already some of these experiments if you came today in a lab. This, well, a noise-making device, we call it a blue wheel. What is it? It's just a pipe. You can look through this. So both ends are open. And if you try to generate sound by moving it at different speed, you can see that you can generate only sound with specific frequencies. You cannot generate any sound with some frequencies in between. Well, why? That's a good question. Another important example. Well, that's not a toy. This is actually a part of old organ, you know. And those are pretty old musical devices. Well, it's not a flute, but it's just to illustrate the principle. We need to make an airflow for this to make a sound. Well, I can make it even harder, but again, you can hear. There are certain frequencies I could generate, and nothing in between. This pipe also is open at both ends, so it's similar to the blue one, but I can close it with a piston, and now it works differently. You hear the difference. So why? We can use this fact to actually play different kind of music. For example, like that. Well, you can make a lot of money with this, but still. And the last one I have, actually not the last, I have one more. I just want to go through all the examples, and then we're going to do a little more boring stuff, you know. Where's my... Well, I don't have it. Well, you know what it is, yeah? What's the name? Exactly. So, that's how it works. And you probably understand that the length of all these pieces is very special. If you make it a little bit longer, a little bit shorter, you generate a sound of a different frequency. So the length, well, first of all, we need to understand that if I hit it, actually I generate waves of different frequencies. But normally, under regular conditions, one is the loudest, and the loudest only we usually hear. In the lab, you could actually measure several frequencies and see the amplitude might be different for different frequencies. That picture we call a spectrum. So you hit it, it generates a spectrum, but we hear normally a fundamental or close to fundamental. Well, this is actually looks like a pipe with both ends closed. How can it work? If you have a pipe with open ends, of course, every molecule can freely move at this end. But if the end is closed, they get in attached to this, and there is no motion here. So you always must have a node here and anti-node here. What happens in between depends on location. Here, it seems there is no motion at any end. Well, there is a hole right here. So if you hit it, this piece of metal excites the air inside, and all the wave with specific wavelength resonates inside this tube, and we can hear the sounds traveling away in all directions. Well, let's go back to mathematics. Well, first of all, in physics, it's very important to draw a picture of the situation you're thinking about. Any wave looks like that, just a set of bumps. So let's say you have a spring attached to two hooks, so these ends are fixed, they don't move. What kind of wave can you generate on that spring? Well, this is one possible solution. Any wave looks like this. So basically what you're looking for is a part of a wave which you can fit on that spring. This is one part. It equals a half of a wavelength. So for that situation, the length of this string must be equal to 1/2 of a wavelength of the wave generated on that string. What other possible situation can be happening? Well, this is another. So that would be this end, and this node could be that end. So in this case, you could generate a wave like that. And it's the same string. So the length of the string is the same. However, now we can fit exactly two holes. Yeah? First half, second half. So two holes. And of course now we can make a natural conclusion. So the next would be 3 halves, 4, 5, etc., etc. So we can say now that if you have a string with both ends fixed, we can generate all the steady waves with this particular set of wavelengths. Number n could be any integer, 1, 2, 3, or wherever. When n equals 1, you're generating the wave of the longest possible wavelength, which means lowest possible frequency. We call it a fundamental. All other waves, we call them harmonics or modes, must have shorter wavelength and higher frequency. And if you want to relate the frequency and the length of this string, well, you need to know also the speed of this wave. It could be a speed of the wave on the string, which is square root of tension over density, or it could be a speed of the sound in a medium, which is roughly 30 meters per second in the air, or 1440 in the water. It doesn't matter. So this expression works always. So you can combine these two, and that gives you a set of frequencies you can generate. Again, when n equals 1, that gives you the fundamental frequency. And if you multiply by some integer, you can get higher frequency. Second harmonic, third, fourth, etc., etc. That's it. All you need to know is how to draw a picture. Now, different example. For a sound wave in a pipe with both ends open. This is how it might look like. This is how the fundamental looks like. Because both ends are open, air molecules must move at maximum possible amplitude. So we have antinode here and antinode here. For any wave between any two antinodes, number 1, number 2, we must have at least one node. At least one. So one or more. So when we have only one node, we have a fundamental generated in that tube. And of course, we can generate the next harmonic and the next one and the next one. For any harmonic, for any of the harmonics, on the end, we must observe antinodes. So, but of course, this kind of a picture is too complicated. It's much easier to represent the same wave by drawing a picture similar to a wave on a string, and that's what we usually do. So, here, the fundamental. We know we must have a node in the middle of the fundamental. And we must have motion with maximum amplitude on each end. But of course, if you remember, the motion doesn't happen like this. The motion happens like this. So, air molecules move with 180 degrees phase difference. And that's how we draw a picture for a situation like that. So this is kind of a snapshot like this. And if we could generate this wave, it would look like this. This motion is up, this motion is happening down, out of phase. So this is a pictorial representation of a wave generated in a pipe. And if we want to generate a second harmonic, well, now we should have two nodes inside. The third should have 3 nodes, etc., etc. So if you look at this picture, we again fit exactly one half of a wavelength into a fundamental, or 2 wavelengths to generate the second harmonic, or 1, 2, 3 halves of the wavelength to generate the third one. So the equation for a standing wave which could be generated in the open pipe is exactly the same as the equation for a standing wave which could be generated on a string with both ends fixed. The picture looks slightly differently, but the equation is exactly the same. All we have to do is just have to count a half of a wavelength, how many halves you can fit. And again, if you know the speed of the sound and the length of this pipe, you can calculate the fundamental and other frequencies. Or vice versa, if you measure the length of this pipe, for example, and using measuring device and microphone, you can measure the frequency. You can use this expression to calculate the speed of the sound. This is one of the many possible examples related to this topic. So, first of all, when we read the problems, we have to understand what kind of situation is happening. Both ends are open. That means this is the equation we must use. Now, here, what's happening is something like this. We are generating several consecutive harmonics. 210, 280, 350, maybe we could generate even more. Well, the first question is, 210, is it a fundamental? I see you have your clicker. So if you think 210 is a fundamental, press 1. If you think no, press 2. If you think it's possible to answer, it might depend on many other circumstances, press 3. Now, before actually I start collecting your answers, I have to switch to the software. So you have to remember your answer, because I have to erase all this. So pick your mind, choose your answer, 1, 2, or 3. Okay? Now I have to switch. And I'm going to test your short-term memory. So again, just to review the question. 210 Hz is the fundamental frequency for this pulse. Yes? No? Nobody knows. And you're supposed to press 1 or 2 or 3. This shows that you press something different, maybe 4 or something else. You're not supposed to do that. All right, numbers. So, oh no, still right. And of course, you're supposed to press the button on your clicker only. All right. Let's see. That doesn't happen very often. Well, you know, just for you to know, technically both of these answers are wrong. Technically, we would have to do some additional calculations to figure it out. There is no direct information. What we do know is that this frequency is the frequency number n or k or m, whatever, it's an integer. So you can assign a number to this particular frequency. Maybe it's 1, maybe not, we don't know yet. However, what we do know, if this is the k frequency, this would be which one? What do you think? If it's the next one, k plus 1, the next one is supposed to be k plus 1. That's supposed to be k plus 1. That's supposed to be k plus 2, etc., etc. We actually don't need many, we just need any two consecutive frequencies to figure out what is happening. So if this frequency equals k times speed divided by 2L, or easier, k times the fundamental, and second one equals k plus 1 times the fundamental is supposed to be equal to which number? Anyone? So 210 equals k times fundamental, 280 equals k plus 1 times the same fundamental. I have an apple in my room, in my office, so whoever gets the answer first gets an apple. So you just have to subtract. Well, easier subtracting in this direction. That gives you 70 equals, well, k plus 1 minus k times the fundamental. K cancels, equals fundamental. So the fundamental frequency equals 70 hertz. Any question? That's how it works. And if we know the fundamental, now we can say it's supposed to be also equal 1 times speed of the sound divided by 2L. The speed of the sound, I think, is given 300, I think. So if you know the speed of the sound, you can solve this expression for the length of this particular pipe. And the next question is, if you take a pipe which is twice shorter, what would be the fundamental for that pipe? Well, for the first pipe, the fundamental is 70. So if your second pipe equals a half of the first one, what is happening to the frequency? If you think the frequency goes up, please press 1. If you think the frequency doesn't change, please press 2. And if you think the frequency should go down, decrease in the value, please press 3. Now, again, take your mind, remember your answer, please.
And now I'm going to switch to sorting point and start collecting data.
If you shorten the pipe, what is happening to the fundamental? The frequency goes up, the frequency stays the same, the frequency goes down. That's the equation you can use. For the fundamental, n equals 1. The medium is the same, so that doesn't change the speed. All it changes is the length. The length is in the denominator of this fraction. If you cut the pipe in half, the denominator decreases. What does it do to the fraction? Increase. Very good. So for this situation, of course, the fundamental frequency increases twice. And of course, now you can calculate any n harmonics, number n, 9, whatever. Any question? Well, now we have to talk about a different situation. So what if we have one end fixed and another end loose? In that case, we must have a node at this end, and we must have antinode at the loose end. Or what if we have a pipe which is closed at one end? In that case, again, we must have a node, no motion at all at this end, and we must have antinode, maximum motion at that end. So we just have to draw a picture of waves we can fit under these conditions. And these are situations. That's the longest possible wavelength we can generate in a pipe like that. A node, an antinode. Well, of course, it doesn't end these. The wave actually is longer. If you look at this picture, it's exactly 1/4 of a wavelength. The next possible stable, steady wave should fit exactly 3/4, because we must have a node and we must have antinode. So we just add in one more node inside. If we add in one more node, we add in a half of a wavelength, and we still have an extra quarter. So 1/4, second quarter, third quarter. The next harmonic has 3/4 fit. 1, 3. Where is 2? It's impossible to generate the second harmonic in a pipe like that. So we have to count only quarters, and we have to use only odd numbers. 1, 3 quarters, 5 quarters, 7 quarters. So this expression describes all possible frequencies we can generate in a pipe which has one end open, one end closed. Again, all we have to do is just draw a picture. Now, if you look at this expression, and you can see the difference. Since we count in quarters, now we don't have 2L, we have 4L. And since we can have only odd number of quarters, this number cannot be equal to any even integer. So it's 1, 3, 5, etc., etc. And now you know everything about 5 like that. For example, here, exactly the same problem, just the pipe now has one end closed, one end open. So you don't have to memorize this expression. You just need to understand how it works. So if this frequency, we know, it doesn't have to be fundamental, could be, but maybe not. But we know that frequency describes the K or M mode. So the next mode, which could be generated, of course, has a higher number. So it has to be equal to K plus what? And again, that's going to be my question to you. What number should we use here for this particular situation? If you think it's 1, press 1. If you think it's 2, press 2. If you think it's 3, press 3. When you understand how it's going on. So if you think it's 4 or 5 or 6, press corresponding number. And K plus what? What did you choose? Yes. Well, you're supposed to have 26, 35, 24 seconds left. Press something. Check your luck. Okay, I think numbers do not change anymore, so we can actually stop collecting data. And pretty good. More than half of the class answered correctly. Since for a pipe which has one end closed and one end open, these numbers cannot be even numbers. So that's supposed to be an odd number, for example, 5 or 11. And this is also supposed to be an odd number. If you're adding 1 to an odd number, you get an even number, which is impossible. So, and it's consecutive, it's the next harmonic, so you have to add 2. So for this situation, the difference between these two numbers equals fundamental frequency times 2. So now 2 times fundamental equals 70, which means the fundamental now for this pipe 35. And now we can know the fundamental, we can answer all other questions. This is just another example of a reasoning like that. Again, one end is closed, and 2 consecutive frequencies differ by 100. So we just said this difference for this pipe has to be equal to fundamental times 2. So the fundamental is supposed to be equal to 100 divided by 2, which is 50. And now, since we know the fundamental, we can calculate the length. We can calculate, well, if you want to design another pipe, let's say open, with a specific frequency, what would you do? Well, if your new pipe should have a frequency different by 20, that means it could be either 50 plus 20 or 50 minus 20. And for each of these fundamentals, now you can calculate the length. But you have to use the correct expression. If you're designing a pipe with both ends open, this is your expression. With 2L. Any questions?